behalf of Space Education and Research Foundation and on my personal behalf, it is my great pleasure to welcome Professor Ashok Ambastha and all the participants from different countries to this event of multidisciplinary webinar that we are going to have. This is the third talk of this series, and today's topic is probing the hidden interior and outer atmosphere of our sun. Before I invite Professor Ashok Ambastha to speak to you on this topic, I would briefly introduce him to you. Professor Ashok Ambastha was born on 17 May 1954 in Jaspur Nagar in India. He did his PhD, his BSc and MSc in 1972 and 74 from Pandit Ravi Shankar University, Raipur. He joined Physical Research Laboratory, which is called PRL, at Ahmedabad as a research scholar in 1975. He received his PhD degree in 1981 by doing research work at PRL, and the degree was awarded by Gujarat University. This work was carried out under the supervision of Professor R.K. Verma. After his postdoctoral work at PRL on numerical experiments on plasmas in magnetic mirrors, in 1983 he joined Udaipur Solar Observatory, which is called USO at Udaipur. This is a unit of PRL under Department of Space, Government of India. He joined this as a scientist and then grew there to the in position and superannuated in 2014 as senior professor. He has worked as member of various national and international scientific bodies. He has guided several students for master's as well as PhD degree. He has published more than 100 research papers in scientific journals, and at present he is an honorary scientist at Udaipur, which is a part of PRL. With these few words, I now invite Professor Ashok Ambastha to join the room, and I will leave the room and listen to Professor Ashok Ambastha. Professor Ashok Ambastha, please.
Thank you very much, Professor Works, for your kind words and for also inviting me to give this talk in this webinar series. I would also like to greet all the participants who are joining us today for this particular talk, which I'll be giving on our daytime, the sun. So the title of my talk is Probing the Hidden Interior and Outer Atmosphere. So first of all, let us see why do we need to study the sun. As I said, this is our daytime star because during the day we don't see any other star which hide because of the high luminosity of the sun. Although they are there, but we can't see them. So the sun dominates. Sun is basically source of all forms of energy. It sustains life, weather and climate pattern on the earth. Also, it is the nearest star to us. It is the governor of our solar system. We had the first talk in this series, giving a talk by Professor Joshi on the solar system. So it governs the entire solar system, which consists of the planets, asteroids, and comets, and so on. And this is the only star which is close enough to us. And because of the proximity of the sun, it is possible to resolve the surface details at very high spatial resolution. So we can see the structure, dynamics, things happening from second to second, minutes to minutes. And also we can study various physical processes on the sun, which is not possible for any other star because they are so distant to us. In fact, after the sun, the next one, the Proxima Centauri, the light takes roughly 4 years to come, while from the sun it takes only 8 years. So that distance is so much that for other stars we can't resolve anything. So the advantage is that by seeing the sun, we can understand other stars, we can understand the birth and so that is why the sun is so important to study. And of late, it has become very important because we also have practical applications due to space weather component. That sun drives the space weather, not just the weather on the Earth, but the entire space weather is controlled by the sun. Because the sun is pumping out so much of radiation and particles related to various types of activities happening on the sun. Some of these things will be covering in this talk. So basically, the plan of today's talk is that I'll first provide a general introduction of the sun, and then we will discuss the visible surface, the surface, outer surface, which we see by our eyes, basically, with some protection. Of course, one has to always take care to see the sun because it is so bright. So the visible surface is the one which we normally see from morning to evening. And that is also called as the skin of the sun or the photosphere of the sun because it emits most of the photons from the sun. Under this skin, which is very thick, very opaque, the solar interior is hidden under the thick, optically thick, opaque medium of the visible surface, and directly it is not accessible to us. And similarly, above the skin of the sun, or the visible surface, there is outer invisible faint atmosphere, which is optically transparent to the photospheric light. So the light comes out without interacting much with this medium, and it is so rarefied that we cannot see it by direct means unless there are special circumstances or special instruments. So we'll discuss this part. And we will also discuss the activity of the sun. Although with eyes we don't see much happening on the sun, but with instrument we see that sun is active from day to day, minute to minute, and year to year. And there are also very highly explosive events which take place on the sun. So these things are the ones which affect the space weather, create stormy conditions, and then we'll summarize them. Okay, so what do we know about the sun from normal observations and normal, for hundreds of years, people have been observing even without telescope, and people have been trying to find out about the sun because it was so important to us, everybody, all the civilizations around the world. So first of all, we know that angular diameter theta, which is around half a degree, is 32 arc minutes. So this is the angle which the sun extends to our eye, and this is simply from observations. We know this is roughly half a degree, okay, and that is an average. I mean, it slightly varies because we know the distance of the sun from Earth varies a little bit because the Earth is revolving around the sun in an elliptical orbit, and from using Kepler's third law and also the rare events of Venus transit, which take place with a very low frequency, something like 125 years. Happens in pairs of events, different sites on the ground. People have determined the distance. Of course, now it is very much accurately determined, and this is roughly on the average 1.5 10 to the power 8 kilometer. That means 150 million kilometer is the average distance of the Sun Earth, which is also defined as astronomical unit. For planetary astronomy, we define astronomical unit as distances of planets. So one astronomical unit is the average distance of the Sun from Earth, which is again 8.3 light minutes. The light takes so much time for the photosphere to come to us. Is sent out from the Sun, takes this much of time. So this is the distance which we know. And once we know the angular diameter and distance, we can find out from geometry the radius of the Sun, which turns out is simply theta multiplied by d. So it turns out to be 700,000 kilometers, which is something like 109 Earth radii. So along the radius of the Sun, you can put 109, the Earth along the equator of the Sun. Another thing which we now know from observations is the solar constant, which is basically the radiation from the Sun which is reaching us, not on the ground, but out of the atmosphere, because on the ground also, but as the radiation passes through the Earth's atmosphere, there are different types of extinction. So it can, depending on place to place, this will change. So from observations which are taken from space, per unit area, the power which comes from the Sun, the radiation comes from the Sun, is around 1360 watts per meter square. So if you take 1 meter by 1 meter area, something like 1360 watts of radiation is falling there, which actually is of interest to the solar engineers, panel engineers who are trying to convert solar energy into other forms of energy. So this solar constant is not a constant because it changes with the activity on the Sun, but it was thought that it doesn't change with time. So once we know this, we can, from inverse square law, and since we know the F, solar constant, we can calculate the total power of the Sun, the total luminosity of the Sun, L, which is 3.85 into 10 to the power 26 watts. So this is an enormous amount of light which Sun is radiating. So this is the luminosity. And again, from Kepler's law, one can find out, since we know the orbital period of our Earth around the Sun, which is 1 year, we can always find out using Kepler's third law, which basically relates the distance and also is proportional to mass. So mass can be calculated into 10 to the power 33 grams, or 333,000 times the mass of the Earth. So it is a gigantic, massive object which controls, because of the huge mass, all the planets around it. So we calculate this. So these are some of the global properties which we can find out. And we can also calculate the temperature from the black body law. It is like effective temperature of the solar photosphere, the outer layer, because we know the L luminosity, and the luminosity is proportional to T to the power 4, which is T is the temperature of a black body, and the Sun can be kind of treated very close to a black body, so it follows the black body radiation law. So we can calculate T from L. These things are known upstairs, I mean, it is stage. So we can calculate T around 5,800 Kelvin. And mind you, this is the photospheric temperature or effective temperature of the Sun. And the composition, I said earlier, that Sun is a gaseous body, because this kind of temperature, nothing can remain in liquid or solid form. So almost everything is in the form of dense gaseous, and around 74% by mass. is hydrogen, 24% is helium, and 2% other elements by mass. And this we know from. So these are the things which we know about the sun. So let us see the structure of the sun as know from various means. So this gives an artistic view, a cutout of the sun. You cannot, but this is giving the internal structure of the sun, and this is the external structure of the sun. And this thin layer, yellow layer, which you see here, is called the photosphere, which you see here on the disk as a yellow orange kind of ball. So this is a photosphere. So essentially, the internal structure of the sun can be divided into three parts. The central core, which is confined within 1/4 of the solar radius, which is very hot. See how we know this? We know from basically mathematical models, and now we have new tools by which we know that sun is very, very hot inside, is around 15 billion degrees Kelvin. The density is very high. If you scoop out 1 cubic centimeter from the deep interior, the density is 160 gram per cc. So it is highly packed gaseous. In fact, because of high temperature, it can be called a highly packed plasma inside, which is basically the central of the sun, where most of the energy is produced. We'll see how it is produced. And that energy, once it is released from the core, passes through the outer layer and central core is the radiative zone where the energy is transferred by radiative processes, and beyond that, from R is equal to 0.76 to R is equal to 1, this is a convection zone where the energy passes by bulk motions of material as a huge convective currents. And on top of that is resting the photosphere. So this is all in brief about the interior. And outside, beyond photosphere, we have this red layer, which we call as chromosphere. Chrome means red. This is a red sphere, which is having low density. Above that, transition region, we'll see what it is. And then outside, which is very difficult to see because of very low density. And from mathematical models, as I said earlier, that inside the sun, due to the high opacity of the photosphere, we cannot see. So mathematical models have been built in the beginning from for last almost like 50 to 100 years, and they have been refined. And from these mathematical models, we know how the temperature and density vary inside the solar interior. You can see here that at the central part, as in the core, the temperature is around 15 million, and then it falls down slowly, and then comes a million degree at the boundary of the core to radiative zone, and then it continues falling slowly the radiative zone, and 0.7 or 0.76 somewhere, what model you are considering, it suddenly rapidly, and at the surface it comes down to around 6,000 degrees, or around 5,800 I said earlier. So roughly, you can, for memory, you can say around 6,000 degrees. And there is a similar curve for density, where the density also follows nearly similar kind of profile, and density falls from 160 grams per cc at the core downwards to roughly a millionth of a gram per cc at the surface. So this is what we have for the temperature and density profiles inside. And what kind of reactions are taking place which drive the central engine? So essentially, we saw that the core is so dense and so hot that the pressure is so high there that the protons, nothing can remain there in atomic form. Everything in basically in the nuclear form. So you have protons and neutrons inside the solar core, and the proton, the majority of them are in the form of hydrogen. That means they are simple protons. So they can join together because of enormous temperature and because of enormous pressure, because the gravitational pressure is so high that nuclear fusion reactions can start there, and essentially two protons, and they can form the deuterium and then helium-3 and release gamma rays in the process, essentially because in these reactions you have two of these. There is a pair of such reactions which finally go into the formation of helium-4. So the end result of four protons joining together is formation of a helium-4. And in this process, if you take the four hydrogens or four protons and calculate their take summation of their mass and then take helium-4, essentially you'll see that there is a mass loss, and from Einstein's relation, we know E is equal to mc square. Delta M is the mass loss here in one pp reaction like this. So we can calculate how much energy will be produced in this reaction, and that is roughly 26.7 million electron volt, and carried by the gamma rays which are released in the process in the center, and then they move forward radiative zone and convective zone. And as the material, as the gamma ray goes outside, it interacts with the dense medium, and in the process loses energy. And by the time it comes out to the photosphere, the gamma ray photon energy has been kind of transformed to cover the entire electromagnetic spectrum, all the way from gamma ray, X-ray of high energy photons to onwards to visible, infrared, and microwave and radio. You can see this is spectrum. So you start with the pp reaction, but by the end of it, when it comes through the sun, it converts into the entire electromagnetic spectrum. And if you take this spectrum, the light which is coming, the sunlight which we are receiving on the ground, and if we image this after dispersing it with a grating or with a prism, we see this kind of, the visible band is very small. But if you just magnify here, you see that it will kind of a spectrum, visible spectrum from violet to red. And if you image this using a imager, you'll see that there are large number of dark lines embedded in this visible light spectrum, and each of these lines cuts to the elements which are present in the sun's photosphere, and the light which is coming from below, from the inside, part of that corresponding to the wavelength of these elements absorbed, and they create these absorption lines that are called Fraunhofer lines, Fraunhofer absorption line. So essentially, these lights, these photons which come from the sun are detected and imaged at different wavelengths, and we get it lines which you have. These lines provide another spectroscopic measurement, which also are used for imaging and the sun in different wavelengths, and we can use any one of these 20,000 absorption lines which have been identified in the photospheric spectrum so far. Okay, so these are the thumbprints of the elements which are also used as the messenger for the structure and dynamics of the sun. Okay, but by the time this light comes to us, it has to pass through the Earth's atmosphere. By the time it reaches the Earth, only visible light can pass through, because the high energy gamma rays, X-rays, ultraviolet, they interact with the atmosphere of the Earth, and they produce ionization. So ionosphere of the Earth is produced, and most of their these high energy photons are consumed while traveling through the atmosphere. So in order to observe the sun, or for that matter any other cosmic object, you have to fly instruments in balloons or aeroplanes or spacecrafts or rockets. So you cannot observe the gamma ray, X-ray on the ground. Thankfully, because if they could come, if Earth had no atmosphere, all these high energy photons could come all the way to the ground, and no life could exist. For these radiations which passes through the Earth, and only visible light can come down to the ground. So there are observatories which observe the sun from the ground, and part of the near infrared can come to the ground. And then again, the infrared part, far infrared, cannot come down because it is absorbed by the molecules which are present in the air. So again, there is a opaque window in the infrared. One has to again use the aeroplanes. Beyond microwave, radio wavelengths can again come down. So the Earth's atmosphere is transparent to the radio waves, and we can have radio telescopes to observe the sun and other cosmic objects. So these are basically two windows, the optical window and the radio window, which can be used from the ground. And for all other wavelengths, one has to go to the space. So in order to study the sun or any other cosmic object, these are different. And essentially any instrument which we can use for observation consists of three parts: the telescope part or aperture part, which collects the photons in various wavelengths, and then all the collected photons are sent to analyzer. It could be image analyzer, it could be flux analyzer, like photographic in the traditional way. It could also be spectrograph if you are using one of the absorption lines. They are also based in spectrographic technique, which measure the magnetic fields. So it goes to these various types of analyzers, and then the result will finally go to a detector. It could be photographic plate or eye itself. You can also visualize, or any photoelectric device, CCD camera of late. So these are of any instruments. Okay, so I am not going to details for optical telescope. There are reflectors, refractors. For radio, there are parabolic dishes, equatorial long parabolic dishes, and so on, which one can use. And there are different types of detectors which are sent in space for X-ray detection or gamma ray detections. So those details I'm not covering in this. So okay, what we do on the surface of the sun, essentially we see the photosphere, which looks uniform if we are observing by the eye. Of course, again, the warning that one should not stare at the sun because you can lose your eyesight. So with some kind of protection, if you see, normally you don't see anything except for this yellow disk. But time to time, some blemishes occur on the sun, which are dark, structures, which we call sunspots. And these were first detected by telescopes by Galileo in 1610. Of course, they had been sighted by visual means by Chinese and so on. And these sunspots are basically high magnetic field areas, high values like 300 to 4,000 Gauss, and they have lifetimes of few hours to few days, and they rotate from the east limb of the sun to the west limb of the sun. And traditionally, people use the sunspots to measure the rotation of the sun around its own north and south axis. So as the sun rotates, the sunspot also rotate, and one found out that close to the equator, those sunspots which occur close to the equator, they rotate faster compared to the sunspots which occur at the higher latitude. Of course, they don't occur beyond something like 40 degree north and 40 south. But with latitude, from the equator, if you take, they give information that sun rotates slower at the higher latitude. At the poles, it rotates very slow. It takes roughly 32 to 34 days to make one complete rotation. So essentially, sun rotates in a differential way because it's a gaseous body. It's not a solid body, and it can take from 28 to 34 days rotation. And we'll see that this actually is the basis for explaining the activity of the sun. And if you see the sunspots with a high resolution, it turns out that they have a highly structured kind of pattern. The central part of the sunspot is very dark, where magnetic fields are extremely high, and outside that, these are called penumbra. This is the umbra. This is the penumbra, where you can see some kind of radial fibrils going away. Essentially, these are the magnetic field lines of forces line toward the photosphere in a canopy form, and in the central part they are going vertically up. They will be far away, and these sunspots are embedded in some kind of convective granules, some structures which range in size from 1,000 to 2,000 kilometers. These are like bubbles because it is convecting from below because of high, temperature at the lower subphotospheric level. So these are the bubbles, convective bubbles, which have lifetimes of only few minutes. So essentially, sunspots are all embedded in such sea of granules. Okay. So you essentially you see these structures, sunspots from time to time. Now let us come back. How do we observe the solar interior? I mean, we could with simple instrument we can see the photosphere, but how do we see or probe the solar interior? It is hidden under opaque, dense layer, as I earlier mentioned. So the knowledge about the interior, I gave you some two profiles. They came from mathematical models, which are basically obtained from the hydrodynamic equations, which one knows by solving or even by mathematically, and also using global observable solar properties as constants. Mainly, people constructed solar standard models with various types of abundance, various types of central temperatures and densities, and then solve them. So that knowledge gave us information about the central temperature and their variation with internal radiation. But the neutrinos which are produced in the solar core through PP chain, they provide a check, and whether these mathematical models are correct or not. And in the beginning, major problem came because of a problem which is related with the flux of neutrinos which we receive on the ground. These neutrinos which are produced in the PP chain, they are very weakly interacting with the medium. So when they are produced in the core, they can come out without interacting with the radiative zone material or the convective zone material. They travel towards the entire space and also to the Earth. And there are detectors for neutrinos on the Earth from many Japanese, Canadian, and so on. And people had been detecting the neutrinos, and it turned out that you don't get the same flux which we expect. So there was only 1/3, normally should have expected from that, only 1/3 of the flux was detected from these detectors. So there was a problem. So people tried to make modification to the standard solar models, and they came out with some non-standard solar models, but that did not solve problems. The problems were created elsewhere. So it was felt that there is no problem with the standard model. Probably there is a problem with the neutrinos itself. So the later on, it turned out that there is another tool called Helioseismology. It is an analog with the seismology of Earth, which provides information about the interior of the Earth. The same way, there is a tool which now we have for the sun using the solar oscillations. You'll see that, which essentially provides nearly direct knowledge of the solar internals. And it has been found now that the results finally match very well with the standard model, except for some departures. So it was found that the problem was not with the standard model so much as the problem with the neutrinos behavior itself, and they required some kind of new physics. The particle standard model of particle physics needed. That neutrinos, they change their flavor as they travel from the sun to the earth, and we only detect one type of neutrinos, not all three types of neutrinos. So we only get 1/3 of them, not complete. So this is one of the resolution which happened because of the helioseismology. So if we put a spectrographic slit on the photosphere at any place, we can see one of the absorption line we can select, which is velocity sensitive, and then we can see what kind of velocities are along this slit, and with time we can see plot them, and turn out that the solar photosphere vibrates in a complex pattern of acoustic waves or sound waves, which have period of roughly, if you see the power spectrum, the period is around 5 minutes, or frequency is 3 millihertz. So essentially, with that kind of period and frequency, sun is oscillating all the time, and the magnitude or amplitude of these oscillations are only few meters per second. It's very difficult to detect unless you have very accurate instruments. So the problem is there that in order to decipher various modes of oscillations which consist of these visible patterns, basically each one of these come because of a superposition of a very large number of modes. And in order to isolate them, in order to find each one of them, it is important to observe the sun's Doppler images over many weeks and months, which is not possible from one place on the ground, because it is a day and night cycle, and as a result have disruption of solar observation. You have only daytime 8 to 10 hours you can observe, there is a night, and then there is interruption. So essentially it creates a problem in isolating these individual. So solutions are there that one can have a network of ground-based observatories around the world, and using identical instruments at various stations, one can observe the sun sets at one place but rises at other place. So you start observing at that place and so on, and then you can join the data and analyze, and then get the options. One go to poles. Rakesh Rao about the polar observing. So one can go to the South Pole, for example, during the period where the sun doesn't set for several months, and one can observe from there. But practically, it has not been possible to get more than of the sun from there, because the weather conditions are very severe there, disrupt the observations. To a sunlit location and observe the all the time, and the data is required to analyze these solar oscillations. And essentially, as I showed the earlier one, those patterns are composed of more than 1 million. Now we know that they are made of more than 1 million modes, superposition of so many modes with different amplitude, different frequencies, and individual modes are basically, defined by 3 integers: L, which is degree, M, which is azimuthal order, and radial order. So these are 3 things, because sun is a spherical object. So these are basically part of the spherical harmonics which we construct. So we can actually, with long data series, one can identify with different L, M, and modes, and each of the modes which we isolate, they are found to be trapped inside the sun at different depths, like an organ pipe. So then also different modes can go to different depths depending on their wavelengths. So those modes which have large L, they can go all the way close to the solar interior, to the core, and get reflected, and then come back. As they are traveling inside, these modes also affected by the internal temperature and density. So as they are traveling, they are affected by, they basically carry the information about the solar interior. So, by identifying these modes, one can reconstruct the model of the sun. Like, a model, let us say spherical body. If you know the density, temperature, you can find out what kind of modes it will sustain. But if you don't know the spherical body's property, you only see the observationally see the oscillations. You can do an inversion and know about the internal structure, density, temperature. So that is the inversion which we do in helioseismology, and then get to know about the solar interior. And this shows you one of the networks which is operational for last 23 years or so, which is called the GONG network, or Global Oscillation Network Group for the solar helioseismology. And this actually uses 6-station network of very sensitive, stable velocity imagers around the world. In Australia, Learmonth, this is India, Udaipur, where I am located, and Bari Islands of the Spain. Then there is a Chile, a station in Chile, Cerro Tololo. And then this one is station in Big Bear, California. And then Hawaii of USA. And then come back. So basically, to answer the scatter, and this has been working for more than 22 years now. Completes very long for a long-term study of the sun. Okay, and this is these are two instruments which have been sent to space. One of them is Solar Heliospheric Observatory, SOHO, which was launched in 2nd December 1995, around the same time when GONG became operational, which is still operational. It is now more than 22 years that it is working. In fact, this will probably go on till December 2018. And very recently, instrument was sent for observing the sun with the prime aim of the Solar Dynamics Observatory, SDO, which is not in Lagrangian, but a place which is geosynchronous orbit, 36,000 kilometers. So these GONG and these instruments are contributing enormous information. So here we see the internal sound speed, and this is the difference of the helioseismic inversion and the standard model. And we see some departures in convection zone at the surface near the core, but otherwise these are very close to less than 0.2% or so. That agreement is very close. You can see the differences in the density, differences in sound speed, which is the temperature, and abundance. So the helioseismology very interesting results. This one is internal rotation of the sun, and from the differential rotation, we see that as you go inside the sun, all the profiles at equator, 30 degree, 45 degree, 60 degree on the sun, they all merge together somewhere near the convection zone. So within the convection zone onwards, the sun rotates as a solid body, although the surface rotates in a differential way. So this is some of the new discoveries and informations about the solar interior which we get. So let us come now to the outer atmosphere, the photosphere and above. After very briefly talking about the internal structure, about the neutrino physics, about the helioseismology, let us come back to outer atmosphere. The outer atmosphere above the photosphere, which I showed in the beginning, the photosphere showed sunspots. Above that, there is a layer called chromosphere, which I showed again as in a schematic way. The chromosphere is roughly 2,500 kilometer thick, and as you see that these are the temperature profile, density profile. From there is a temperature minimum in the chromosphere, then it rises up, and then it suddenly goes very fast, increases very fast in a very narrow region, which is called transition zone, and then keeps increasing outside. The temperature slowly increases outside in the coronal medium. Similarly, the density falls very rapidly through photosphere to chromosphere, and then an abrupt decrease in the transition zone, and then it keeps slowly decreasing with distance. So you can see the temperature of the corona goes to around 1,000,000 degree. You can see the scale here, 10 to the power 6 degrees. This is 10 to the power 3 degrees. Similarly, these are the densities here in kilograms per meter cube. So one can see how it varies. The temperature is very high as you go away from the sun, which is one of the major problems people have been trying to understand, how the photosphere is 6,000 degrees, but temperature of the chromosphere increases and then corona goes to 1,000,000 degree. So what is the mechanism for the heating of the corona? That is one of the major problems for which people have been working for a large number of years. So this is the image of the chromosphere. Just above the photosphere, we see that this 2,500 kilometer thick layer, essentially the temperature is little bit hotter than the photosphere. Instead of around 6,000, is 10,000 to around 20,000 degrees. And you can start seeing structures, bright structures around the sunspot, dark sunspots. They have bright structures around them, which are information giving you about the temperatures around the spot, which is higher temperature means hotter, so brighter. And then a lot of other structures in the entire chromosphere, which we are not able to see in the photosphere. So you start seeing the effect of the magnetic field in these layers. You also see some longer filament-like structures which are dark. These are gaseous ribbons. If you magnify them, they look like this. Near the sunspot, these long ribbon-like structures, they meander through the chromosphere, and these are accumulation of gases along some kind of magnetic loops or magnetic tubes. They accumulate matter, so temperature falls down and their density increases. So these are called filaments, but if you see them at the edge of the sun, they look brighter. This is the extension of the filament to the edge. You can see that this is now, because seen against the dark background of the sky, they look brighter, but here they look darker. So these are prominences or filaments which remain there for several days, sometimes weeks. As the sun rotates, we can keep following them with minor changes in their structure. But sometimes when the magnetic balance which holds them together to the sphere is kind of disrupted, so they can erupt out with very large speeds, exceeding the escape velocity on the sun, which is 650 kilometers per second, and then they can go into the space and form other disturbances. This is the solar transition region, which I showed you earlier, that above the chromosphere, change in temperature and steep decrease in density. So the temperature goes from around 25,000 degrees in the lower transition region, that means upper chromosphere. So basically transition region is nothing but a small thin layer of gas which is between the chromosphere and the corona. So the temperature in this region changes from 25,000 to roughly 500,000 degrees within just 1,000 kilometer height. The temperature becomes so high that now it can start ionizing. The more ionization can occur, and also the magnetic field becomes more important there. So it can start emitting in ultraviolet and extreme ultraviolet in the transition zone. So this you cannot see from the ground. You have to go to space, and these two examples are shown here. The lower transition region, this is the upper transition region, where you can see more structures. Like here, this is a chromospheric, very close to chromospheric pictures, but you can see that more structures are seen to show that far off spots of can be connected by some kind of magnetic loop. So these are taken from SDO some time back. So these are some examples. Above the transition region is the corona. It's even more fainter, even more rarefied as compared to the transition region, and the emission of corona is more than a million less than the photospheric intensity. So because of the photosphere, you cannot see transition region, you cannot see the corona, and there are forbidden lines also which show up as emission line at the time of eclipses when the photosphere is completely covered by the moon. Then you can see it for a very short time. You can also see the transition region for a few minutes. So in that time, people have discovered, some emission lines from the corona, and one of them is called wing line, which is because of the iron, highly ionized iron, which emits at 5,300 angstrom. Initially, because this is not seen on the Earth, it is forbidden. In the labs, it's very difficult to see them. So it was seen in the sun because sun is so rarefied, but it is highly probable that such reaction can take place for many other things. So it was discovered, and it was called coronium because it was not known what it corresponds to because it's coming from corona, so coronium. Similarly, helium was discovered during one of the eclipses in 1868 from India, something like from this year, and it was named after Helios. So helium gets the name from the sun because it was discovered during the eclipse of the sun. So there are, essentially 2 or 3 ways of observing the corona. That first of all, the photosphere has to be covered for blocking the photospheric emission, so that you can start seeing emission from the corona. Or you can also use one of these lines, like green line, forbidden lines, which is basically corresponding to the emission from corona itself. So this is called, and this is K corona, because the white light image which we see during eclipse is essentially the scattered photospheric light by the free coronal plasma electrons. One can also create artificial eclipses at high altitude observatories. There are some observatories in on the ground, like in Hawaii, around 4 kilometer altitude, from where one can create artificial eclipse, or one also can do the same from space. Then there is a more recent revolution which has taken place in observing astronomy, is that one can detect an image, high energy ultraviolet, extreme ultraviolet coming from the corona and X-rays, both by thermal and non-thermal. Of course, I told in the beginning that sun is emitting as a black body. Essentially, that is the thermal part, where the signature from these X-rays or radio is very small. But non-thermal means in the plasma of the corona itself, the emission of these wavelengths can occur. Even radio can take place. So one can observe the radio sun from the ground, because that is the window. From space, we can see these. So some of the pictures I show here. This is a K corona. This is a composite of a large number of images taken from Norway, Svalbard, for March 2015. So around 34 images have been combined, images taken in different exposures. So they show that the sun is confined within this half a degree, but corona extends to large distances. So essentially, this is a continuous sun's structure. You can see the outer atmosphere all the way in space for several solar radii, which you can see during such eclipse. One can also see all the time from space the X-ray images or ultraviolet images of the corona, and one can see many new things on the sun which normally not seen otherwise. That coronal holes, that dark, large dark structures in X-rays where no emission is there, and you can see photosphere, because photosphere is not emitting X-rays, so we can see the lower part. And these are active regions, the spots close to sunspot where we can see many loops related to them, connections we can see, and the halberd streamers we can see off the disk. So a lot of such things which are very dynamic. So essentially, from all observations which we gave you so far, sun is variable, inhomogeneous, active, explosive at all levels from corona. Even in photos, we saw that time to time sunspots occur. So even there, we saw some kind of inhomogeneity. And these are enormous number of structures which are obtained from SDO, in sort of connections between far away active regions which are there. Active regions are again here, yes, magnetic loops and all that. So essentially, in this layer, magnetic field is very, very dominant in the corona. Essentially, a plasma beta parameter which we define as a pressure, plasma pressure divided by the magnetic pressure. For corona, this beta is much, much smaller compared to 1. That means plasma pressure is negligible as compared to the magnetic pressure. So in the corona, the magnetic fields, they start dominating the structures and show up the variety of things which we see. And we just very briefly tell you about various types of activities. We see that in certain areas of sunspots, time to time there are sudden eruptions of energy which range from 10 to the power 26 to 10 to the power 32 ergs in a few minutes to few hours. And these are called solar flares, which enhance the radiation, and also they can produce X-ray and gamma rays for short time connected with these events, and they release energetic particles which are emitted out, and they can disturb the space around the sun all the way to the earth. And then these are the eruptions of the filaments, these are called basically explosive events, explosive flare, explosive filament eruptions. They can occur within few minutes to few hours, half an hour or so, and they also pump out enormous amount of gaseous material into the space. So these are they can lead into coronal mass ejections, which now we see from space by obstructing the central part, and we can see that some very large blobs of gases can come out from the sun and travel into the space with speeds of 100 to 2000 kilometers per second into the space. And some of them which happen near the central part of the sun, they can come towards the earth. They are called halo CME. CME is coronal mass ejections. So these were detected in the early 1970s from the Skylab. And now, of course, on routine basis, we are detecting them. So we have solar flares, solar filament eruptions, or prominence eruptions, coronal mass ejections. These are the explosive events which take place on the sun, depending on different phases of activity of the sun. And not just that, from the coronal holes, very fast streams of winds coming of charged particles, which are streamed off from the sun in order. In fact, they are streamed off in all the directions away from the coronal holes also, but they have slower speed, around 300 kilometers per second. From the coronal holes, we get high speed streams coming out with high 800 kilometers per second, and time to time they carry the coronal mass ejections. We can have more than 2000 kilometers per second. So essentially, the solar wind is nothing but a wind of charged particles, which is a result of the expansion of the corona in all directions away from the sun, and it has been found to be highly non-uniform around the solar latitude, which has been now mapped by satellites which are polar over the polar away from the ecliptic plane of the earth. They can go, and so one has found these things. So these are the things which can affect the space weather in a variety of ways. in this manner that solar wind comes out and then it strikes the magnetosphere around the Earth. This is the Earth here. Of course, this is not to the scale. It has a magnetic field around it, and it's like a dipole, but because of the interaction of the solar wind, the daytime of this magnetosphere is compressed, while the nighttime of this magnetosphere is extended to long distances, and the charged particles which are coming during flares or CMEs, or all the way because of all the time because of solar wind, part of that, a fraction of that can be trapped from the night side and also leak through this and uh, get into the polar latitudes on the Earth, and then they can show up as auroras in the northern auroras and southern auroras borealis or aurora australis, because as they come, they impact on the Earth's atmosphere's atoms and ionize them, and then show up as a bright light, during this. So they are basically the signpost of high activity, and they can also, these activities can affect in various other ways, that they can disrupt the power grid at polar locations, they can disrupt radio communication or even GPS navigation, because they create geomagnetic storms in the magnetosphere. Even ionosphere of the Earth gets some kind of changes, rapid of solar activity. It can create anomalies to the satellite instruments, because the charged particles which are released from the sun during disturbances, they can impact on the instruments and create disturbances. They can even break down, and the satellites can slowly lose their height and come down on the ground. So they can create the reduction in the lifetime of satellite also. And also it can affect the astronauts. If they are outside the space station or something, they are normally told to get inside if there is expected to be a large activity in the sun. So these are some of the things, which hazards which we have from the space weather, because of which space weather has become a very important topic. Of course, the sun doesn't behave as a constant source of activities. If you plot the number of sunspots with time, one can see that they vary with time in a cyclic manner, which has an average period of 11 years. Of course, it can vary for some cycle from 8 years to some other cycle to 13 or 14 years. And one can see that magnitudes also change from time to time. Very high activity levels seen here as recently as in 1959, this very high activity was seen. And there were also some time when sun was not very active as far as sunspots were concerned. In the early period of rudimentary sunspot missions in 1650 to 1700, there was a Maunder minimum, very few sunspots. And then the numbers of sunspot cycles are counted from around 1750, cycle 0, 1, 2, 3, 4. So cycle number 23, cycle number 24, which was the recent cycle. So you can see that there is an activity cycle of the sunspots connected with the sunspot. In the same way, the flares can be plotted, and they also show the same kind of thing. Even the solar constant plot, which is now called solar irradiance, one can see that that also changes in phase with the solar cycle. For last many years, from 1975 onwards, different satellites have been observing the solar irradiance, and one can see that it goes to some kind of variation. That variation is not very big, only 0.1% the magnitude you can see. But even this can cause climate variation. They can impact climate variation to some extent. So these are, in brief, some of the features which I wanted to discuss. And in summary, I should probably just mention various things which I try to cover. That it is required to observe the sun in different wavelengths. In fact, many wavelengths, both from ground and space, in order to obtain a detailed three-dimensional map complete solar atmosphere from the photosphere to the chromosphere to the corona. One wavelength is not enough because you only see. Similarly, it is very important to measure the magnetic field of the, because its interplay with the solar differential rotation causes that plays a major role in solar activity cycle, also for storing and releasing of energy in active region, which is then available for explosive solar events. So it is very important. Also, velocity is very important because we use this data for helioseismology. Although for the photosphere, these observations have been improved a lot, but in the chromosphere, in the corona, measurements are still in infancy, primarily because the chromosphere and coronal spectrum, the absorption lines or emission lines are very difficult to see, and also they are very broad for measurements to be of any use. So there are some other methods which people are devising, which I did not discuss. For corona, magnetoseismology, where different types of waves and instability in the coronal plasma people are detecting, and they are providing information about the coronal magnetic field and also coronal density. Apart from that, measurement in high resolution, both in time and in space, is needed in order to see very fine structure, the basic physics of various things happening, like how flares occur. They occur in coronal height where resolutions are low, for magnetic field. So it's very difficult to observe there, but is required to improve the spatial and temporal resolutions both. And we have seen that for probing the deep solar interior, neutrino physics, helioseismology, they are important tools. They have even made a major role in resolving the problem of neutrino deficiency and also in improving the knowledge about the neutrinos. This I mentioned just now. And whatever we have learned from the sun's seismology, helioseismology, now this is also being extended for other stars. We have learned a lot from helioseismology for the internal structure of the sun. So same in analogy with the helioseismology, people are now developing asteroseismology. I think someone is going to give a talk tomorrow on asteroseismology. We'll see how it is being extended to other stars to understand their structure. Very recently, a new space telescope has been launched, which is called Parker Probe, in the name of famous physicist, solar physicist Eugene Parker, on 12th August 2018. And this is going toward the sun, and it is going to observe the sun from within the corona, from a distance of 5 million kilometers from the photosphere. So essentially, it will be immersed in the corona and observe the local conditions, also the transition zone and chromosphere and so on. And hopefully, it will contribute to the resolution of heating mechanism of corona, which is one of the outstanding problems. And so there are many more exciting times and discoveries in the future are expected. So I think I'll stop here. I think I have already taken more time. Unfortunately, in between, we lost the link for 5 minutes or so. So there was some disruption. I hope you have questions. So I'll be glad to. Somebody asked me the separation between various wavelengths of AIA of SDO. Essentially, there are around 13 different wavelengths which are used by SDO, and they cover all the way from photosphere to the corona. So one can actually just check the wavelength interest, and one essentially can see that the photospheric observation, the chromospheric observation, transition region, and coronal region, they're all covered by various wavelengths. So it covers the entire kind of atmosphere. And as far as somebody asked me, how does CME affect the satellites? I conveyed the CMEs are basically large plasma blobs which are released from the sun, and then they pass through the interplanetary medium, one can now actually monitor them using different instruments. It could be in situ instrument from satellite, but also from the ground using radio telescopes. One can see the interplanetary scintillation, how they are going. And in fact, they lead into some kind of disturbed stormy condition. So when CME takes place, when they hit the satellite, they can cause interruption in the satellite instrument. So sometimes the people switch off the satellite instrument for some time. So communication also are affected when whether the satellite itself is concerned, and also as far as the disturbance in the ionosphere and magnetospheric conditions, they can lead into disturbances, magnetospheric storms we can have. So they create a disturbance in the satellite communication. So, and I see Professor R.P. Dahiya, his old friend from PRL. I'm also glad that he attended this talk. Somebody says, can we correlate solar rotation with the solar constant or solar irradiance? These are two different things. Solar rotation is not directly connected with the solar constant. As you saw, that solar constant or solar irradiance, now we should better call it solar irradiance because it is not precise is not a constant. That has a variation with the activity cycle, not with the solar rotation. Solar rotation is not changing, while the solar activity is changing, and we saw that it changes in phase with the solar irradiance changes in phase with the solar activity. Okay. Yeah, I agree. I mean, essentially, the idea is to, Dr. Dahiya says that I covered lots of things. Each one, like helioseismology itself, is a huge topic. So one could spend a lot of time on helioseismology. I just brushed upon various topics because idea is to give the challenges which one faces in observing the inside and outside the solar structures and activities. So, so that is the idea, and in fact, as far as solar reactions are concerned, Dr. Dahiya has another question that how could one study solar reaction? So essentially, it depends what kind of reactions will go on. This depends on the type of the star. Solar type stars are mostly having PP reaction. This because the abundance is highest for the hydrogen there in the central part, and as the reactions continue consuming more and more hydrogen, the other reactions will become operative. To a very small fraction, there's a CNO cycle which is involved, but for sun it is very, very insignificant. So most of the energy which we receive from the sun is because of the PP reaction. But there could be other star in which the hydrogen has become very low in abundance. So the helium to lithium onwards, other reactions will take over. So this is another major problem or major topic of interest one can have. Okay, and can substorm cause the same damage as much as CMEs and flares? So actually, the substorms are related to the Earth's magnetosphere, while the CMEs and flares are related to the sun itself. So these are the sources of disturbance of the space weather, while substorm is a result of some of the minor things. So substorm is can happen because of some of the smaller flares on the sun or smaller sunspots or some fast stream coming from the sun. So essentially that will be that is the end result of these disturbances. So one cannot say that this is CM related to CME CME is connected to to the sun while substorm is Earth. Okay. Okay. Somebody says some Swarna. How does the equator of sun and polar region revolve at different speeds? Some revolute. I don't understand. There's revolve probably. So this I told earlier that sunspots gave the early indications about the differential rotation of the sun. When you measure the rotation of the sunspot at different latitude, you found that it is varying. But now one can measure the rotation all over the sun at high latitude also using a spectroscopic method, because you can see, from the Doppler effect, you can see at any latitude or any rays on the sun how things are rotating, and it has been confirmed that the sun rotates in a differential way. And I told that the equator rotates faster. It takes roughly 28 days to take one full revolution around the north-south axis, while the polar region takes around 32 to 34 days. Of course, very close to the poles, you cannot measure it very well, because you are only observing tangentially. Okay, so I hope it answers you. Okay, so I don't see any other question. So yeah, I think again Swarna has this whether it is only for gaseous body. You see, I mean, it probably is also related with the densities, as from the helioseismology we found that as you uh, measure the rotation of the solar interior, more and more informations are giving the information of the interior rotation, and as you go inside the sun, the density increases, and it starts behaving like a solid body in the central parts. We saw that the differential rotation, all the profiles, they merge into one profile, which is a single profile, and there's hardly any change with the depth after a certain depth inside the sun beyond the solar convection zone's base. So it behaves, although it is still gaseous inside, but very high density. So still, it behaves like a solid body. In the case of Jupiter, again, it's a gaseous. I do not know exactly how at different depths how the Jupiter's atmosphere is rotating. So I'm not the right person to answer this question. Probably I'll defer it. And yeah, I think Dr. Dahiya has another question about any correlation between global warming and solar activity. I had a slide on this, that this has been a major, about global warming. Yesterday also, Rakesh Rao had mentioned that if the Antarctic ice shelf starts melting, it can create a problem because of global warming. It can happen probably, and some of the coastal areas can get submerged after some time. So people have been studying the solar activity and global warming, and thankfully, it seems that the recent data shows that although in the early times the technological advancements were not as much as it is now, uh, the changes in the Earth's average temperatures were kind of going hand in hand with solar activity cycle. But in the last 20 years or so, it has been found that sun's activity level has been going down. In fact, the magnitude or amplitude of the solar activity cycle, cycle number 23 was much lower compared to 22, 24 was much lower than 23. and it is expected that solar activity will go further down in the next cycles. But the trend of the global warming continues. So that means there is not a direct relationship, and global warming seems to be mostly a man-made problem, not the sun. So sun cannot be probably. It seems that sun cannot be blamed for the global warming. We ourselves are to be blamed. Okay, Miral is asking about solar cycle 23 being less active than 22. As you saw that, the past cycles also you saw that sun, of course, there is a dominant activity cycle is of 11 years uh, from the sunspot curve. And you also saw that with time you had Maunder minimum, you had some maximum periods also. So sun's activity cycle basically is a superposition of different large activity cycles also. So you see the sum of all different cycles, and as depending on which period you are seeing, you saw that in the past there were many such places where the amplitude of cycles were much lower. In Maunder minimum, there were hardly any. So it is nothing strange. I mean, the sun is behaving in this manner in the past, and it will continue to work like this in the future, and it will show the dominance of different cycles when they are superposing. The on time series will show its effect. So it can happen again that you can probably, I mean, there are people even saying that probably we are going towards another minimum like Maunder minimum. So we don't know yet, because there in the past also it happened that it did not touch to low, very low sunspot cycle like Maunder, but it had gone down to very small cycle. So that way I think sun is behaving as it was earlier. Okay, so I think that's so. I think at the end, I think I should again thank all of you and bear with me for a very quick overview of the sun. Of course, people who are interested in solar physics, they can see different topics in more details. In fact, it is a very long process. I mean, each of these topics about the internal structure, about the outside activity, even the coronal seismology and so on, they are all different huge topics, and they require a lot of deep studies. My idea was only to introduce to these new things which are happening. So thanks again for your